Jo, tak to mě stačí, to teďka přijde, že takhle, jo. Ladies and gentlemen, I'm very glad that I have the possibility to welcome you to today's lecture, that you accepted our invitation to the lecture, which is organized by Czechoslovak Tech Users Group. And I'm very glad that Jonathan Q, the author of XeTeX, accepted our invitation and decided to come to Czech Republic and later on to Brno. And I will ask him to start, probably.
Okay, first of all, I'd like to thank you very much for the invitation to come here. We spent yesterday exploring a little bit of Prague. You have a beautiful city, and I'm sure if we had more time, we'd find many more things as well. So it's a privilege to come and visit your country, see a little history and culture. But I'm here today to talk about XeTeX. What I hope to do is to introduce XeTeX to people who perhaps don't know much about it or know anything about it. You know about TeX. This is the Czechoslovak Tech Users Group, so of course people, our tech users, know about TeX. But I'd like to talk about what XeTeX brings to the tech world, which is, first of all, support for the Unicode standard, the modern encoding standard, not just for English and European languages, but for all the languages of the world. And then support for OpenType fonts and TrueType fonts, modern font technologies that didn't exist when TeX was invented. And at the same time as bringing these things to the tech world, XeTeX also, I hope, makes them simple to use, takes away some of the complexity that has been a problem for tech users, particularly trying to work with different fonts for many years. So just a little bit of history. XeTeX has existed now for several years. The first public release of a XeTeX system was in 2004. At that time, it ran only on the Mac operating system. You'll see I'm running an Apple machine here, and XeTeX still runs on the Mac system. But it now has gone further than that. But when I first released a XeTeX package in 2004 for the Mac, it had support for Unicode, and it had support for all the fonts that were installed on the Mac system. And I think that's what excited Macintosh tech users, that suddenly they couldn't just use Computer Modern and maybe Times Roman and Helvetica and a few other fonts that they had tech packages for. They could use any font that Apple provided on the Mac system. And I was amazed how much excitement that caused. People felt that they'd been missing this for so long. We also had access to some of the advanced features that are in modern fonts, and we'll show just a little bit of that later, what that means. So a year later, in 2005, XeTeX had advanced from 0.3 to 0.9. You can do anything with version numbers, so you can make it sound like you're making a lot of progress. But at that time, we had support for OpenType as well as for Apple's own technology. OpenType is the cross-platform technology for modern font rendering. And several users in the community had started to write LaTeX packages to work with XeTeX. And so it was becoming much more accessible, much easier to use. In 2006 was the first release of XeTeX for Linux. And so that's when XeTeX escaped from just the world of the Macintosh and became a wider product that can be used on Linux and all kinds of other systems that are like that. And then just a couple of months later, a Windows version was produced by Akira in Japan, who builds Windows binaries of all the different tech products. I was expecting that I was going to have to struggle with Windows build systems and projects and work out how to build a program on Windows. But by releasing the Linux version openly, Someone else did it, and that's the wonderful thing about this open source software world. You don't have to do everything yourself. I'm very happy for that. This year, 2007, was when XeTeX became part of the whole TeX Live package. So if you run TeX Live 2007, if you install that, XeTeX is included, it's there. So it should be available to anyone who wants to try it. And many people, of course, have helped to make that possible within the whole TeX Live team. Okay, let's talk a little bit about some of the basics of what XeTeX does, how it changes the TeX world. When Knuth created TeX in the early 1980s, it actually read 7-bit text. It had a 7-bit text input system. And Knuth felt that was all you really ever needed, that a keyboard that could produce 8-bit text with 250 characters would be unusable. 7-bit text was all anyone would ever need. That's what TeX supported. And so then we had conventions like typing lots of hyphens to get a dash, because a long dash wasn't in the encoding itself. You had to have some other way to create it. The same with quote marks. For accents for European languages, he invented these escape sequences, backslash quote, backslash tilde, and so on. And that worked well for what he needed, which was to typeset English and sometimes to put a foreign name in there. So that was enough for the English typesetting needs that Knuth had. People, of course, started to use TeX for other languages as well, for European languages. And so they would extend these conventions. In Babel, in the LaTeX world, we very often have additional active characters, like the double quote mark, to make it easier to type the European letters that people need to use. But TeX originally was a 7-bit system. It had access then to 8-bit fonts, but it was at heart a 7-bit system. At the end of the 1980s, TeX version 3, Knuth admitted he was wrong, and 8-bit text was really the standard in the computing world. 7-bit was not quite enough. So TeX was extended to have 8-bit support. And that made it easier to support all the European languages. We could support the national character sets of Eastern European countries, Western European countries. They're different. In France, they have a slightly different character set from in Poland or the Czech Republic or Russia. Well, Russia's Cyrillic, that's different. But at least it was a little easier to support the accented characters of European languages. But if you needed real multilingual typesetting, if you needed to support not just one national language, but several different languages in the same document, it's still very difficult to find an 8-bit encoding that gives you all the characters you need. And if you add non-Latin scripts, Asian languages to that, it becomes a very complex situation. And of course, TeX users are very creative, very resourceful. They came up with answers to that with preprocessors and complex macro packages, custom encoded fonts, a lot of different solutions. So almost any language you want to print with TeX, you can. There's a package to do it. But to try and put several of those languages together can be very difficult. To try and make them work with other macro packages can be very difficult. Okay, then Unicode came along. And Unicode aimed to provide a single encoding for all the world's scripts, all the world's languages, so that any character you need for any language has a defined code point, and you don't have to switch between different code pages. You don't have to know which code page this word is in if it's different from the next word. It's a single unified encoding that's designed to support all the scripts and all the languages of the world. That makes data interchange much easier. If you have a Unicode text file, that's all you need to know. It's Unicode text. You don't have to think, was this code page 1252 or 1254, or was it ISO 8859-1? There are so many of these 8-bit encodings, and they're all slightly different. And if you guess wrong, you'll misinterpret the text. You'll print it wrong. Unicode eliminates all that by standardizing on a single encoding. And Omega is the first TeX version that aimed to support Unicode. But Omega, I have to say, never really became widespread, never really became stable and reliable enough, I think, for the TeX world to adopt it. There have been a few people working with Omega, using Omega, but as far as I've seen, it's never really been widely accepted. The other thing that happened is that the Unicode consortium, which defines the standard, fairly quickly realized that even a 16-bit character encoding isn't big enough. There are more than 65,000 different characters in the world. And so Unicode today is not a 16-bit character set. I still meet people who make that mistake, and it is a mistake to think of Unicode as a 16-bit character set. It's not. Unicode is bigger than that. Unicode today, Unicode version 5, I don't remember the exact number, but it defines somewhere around 100,000 characters. So you can immediately see that doesn't fit in 16 bits. And the number is still growing. Unicode 5.1 has just been announced in beta release, and that will add a few more thousand characters to the set. And beyond that, there will be more. So to represent Unicode text, it's not an 8-bit encoding, it's not a 16-bit encoding. You can represent Unicode characters in 21 bits, but of course we don't do computing in 21-bit units. So there are several different ways to represent that. The common one that people usually work with is what's called UTF-8. People often assume UTF-8, Unicode mean the same thing. They don't really mean the same thing. Unicode is the encoding which defines all the characters and gives them their code values. UTF-8 is a way to represent those code values in 8-bit bytes. So a single character may be a single byte, it may be 2, 3, 4 bytes. But UTF-8 is a way to take those Unicode values and encode them into a stream of bytes. One of the really neat things about UTF-8 is that the original 7-bit ASCII set, back where Knuth started, is represented exactly the same way in UTF-8 as it was back in 7-bit ASCII, the same byte values. And the great thing that means for me developing a Unicode version of TeX using UTF-8 is we can still read all those old macro files that were written in 7-bit ASCII text, and they still work exactly the same. We don't have to convert all those macro files to anything different before we can use them. So both XeTeX and now LuaTeX, which I'm sure people have heard about as well, the kind of the descendant of PDF-TeX, both support the complete Unicode character set, and they both read UTF-8 Unicode files. Actually, they process them differently inside. LuaTeX, for those who are interested in technical details, LuaTeX works internally with UTF-8, at least that's my understanding from talking with the developers. XeTeX, on the other hand, internally works with the Unicode character values as 32-bit individual characters. So it's always a single unit. But that's an internal architecture difference that doesn't matter. As a user, you don't see that. It's all Unicode characters. So let's look at what it looks like to typeset Unicode text with XeTeX. Of course, we have access to all the accented characters you could ever wish for in Latin script. So I picked random sentences off of the internet in some different languages with different sets of accented characters. But with a Unicode font in a Unicode version of TeX, they all just work. There's no need to switch input encodings. There's no need to specify font encodings. It's all just as transparent as typesetting ASCII text used to be in the old days. So any of thousands of accented characters that are in Unicode will pass directly through the XeTeX system, just like an ordinary English letter A works in TeX. But it's not just accented Latin characters, of course. There are lots of non-Latin characters in Unicode as well. In the example here, I've specified different fonts for the different script examples. The reason for that is that it's still the case you won't find a single font that has every Unicode character in it. There are some good technical reasons why that's probably never going to happen. So you will still have to choose an appropriate font for the Unicode characters you want to print. But having chosen a font that's got the character, there's nothing else to do. It just works. It's just text. So there's probably spelling mistakes in here, but okay. Yeah, the accent there looks a little odd. But any Unicode character should be printable through XeTeX with no special effort. Now, the interesting case comes with scripts like Hindi or Urdu that are in here, where there is actually complex behavior that goes on. The characters are not just printed individually. If you look at the second sample line, the Devanagari, there's a big difference between the input text that shows the individual characters that were entered in the source and I wonder if my pointer works here. Yes, it does, okay. These are the individual characters entered into the source text, but the rendered form is actually quite different. But that's the correct behavior of Hindi script. And that happens because the knowledge of how to do that is built right into the font that's being used. So again, there's no TeX macro programming going on. There's no preprocessor like the old devnag package for TeX. It's purely text, and it renders correctly because of the Unicode definitions of the characters and because of the font that contains the right rendering behavior. The same with the Arabic script, or this is actually Urdu down here, that's being rendered correctly from the individual characters that were input. So let's get rid of the navigation there. Okay. One of the challenges for the TeX world has always been the languages like Chinese and Japanese, the Far East languages that have tens of thousands of characters in the character set. And the CJK solution to that has been to break fonts up into lots of little 256 character fonts. And again, there's complex macro processing that goes on. But with Unicode, none of that is necessary. A Chinese character is just a Unicode character, like an English one. So you can put them into macros, you can use them as text, and they will print just as easily as English letters. So by moving to Unicode, we break free of the limitations of an 8-bit character set, a 256 character font. We expand the capabilities of the system to support all the world's languages much more easily than the standard TeX ever was able to do. Here's another neat example, is that we can take Chinese text and we can even render it vertically, which is the traditional way of printing Chinese. As far as TeX is concerned here, it's still just building paragraphs the way it usually does. Then we just turn the whole box on its side in the output routine. And there's a sample that you can actually get off of the XeTeX website that shows the whole file rendered this way. But the goal of XeTeX is to make it just as easy to deal with Chinese or Arabic or Hindi as it is with English. We shouldn't put these other difficult languages at a disadvantage. Okay, then let's also talk about fonts. TeX is about typesetting, and typesetting uses fonts. So we need good control of the fonts that will be used in a document. But traditionally, I think many TeX users have found it difficult to deal with fonts. And the result is that most TeX or LaTeX documents are printed in computer modern because people don't know how to change that. Or they may be printed in Times because people know how to load the Times package or the Palatino package. But there's very few choices. And going beyond that intimidates average users. Of course, there are experts who can do it, who can take any font and make it work with TeX. But how easy should it be, or how difficult should it be? Well, computer users today are used to graphical interfaces, and you want to choose a font, you bring up a font dialog and you find the font. Its name is in the list, and these are off of some various different systems. This is the sort of thing that users expect to see. They expect to see the font name and choose the one they want. In TeX, what do? Well, we say things like this, where the font names are a little bit confusing. Those of us who've been in the TeX world for a long time are used to these, of course, the famous Carl Berry font naming scheme. Carl cringes every time he hears that because he feels like it's a terrible thing that we shouldn't still live with, but we do. So if you know the magic abbreviation for the font you want, you can load it in TeX. But wouldn't it be easier if you used real names? Those are the names that you see in every other application. Those are the names that XeTeX lets you use. So instead of saying font helv equals PHVR8T, you can say font helv equals Helvetica. I think that's a little friendlier for a user who might want to use a font and hasn't thought about how to set it up before. And of course, we can go beyond the names that have standardized TeX abbreviations, and any font that's on the system, we can name it and use it. So not just the top few there, but any of the others that I've listed here would work on my computer because those are fonts that I have installed. Not only can we use all the fonts just by asking for them by name, but we can access their advanced features. A font today is not just a collection of character images, little pictures of characters. That's what fonts used to be at one time. But it can go beyond that now. Modern fonts have features like small capitals or swash glyphs or alternate sets of numerals. The way that used to be done was with what Adobe and others called expert sets, where you'd actually have a different font that had the old style numerals in it, or a different font that had the small capitals. And so as a typesetter, you had to know how to access the expert set font and which characters in it to use. But now this is all built into a single OpenType font. If you buy an OpenType font from Adobe or download a free one from a modern developer, these features will be built into the single font, and it's up to the application to know how to access them. And so XeTeX allows you to do that. Whatever features are in the font, you can access. So I have some examples here of declarations that load. They all load the same font, Adobe Garamond Pro. First, just in its default form, but then with the small capitals feature, then with the old style numbers feature. And the result is that the font appears differently. The glyphs that are rendered are different. So as a TeX user, you have access to all the features that the font manufacturer has chosen to put in that font. Another feature that is automatically supported. A lot of this happens because there were ways to do it before, but it required a lot of configuration. The idea with XeTeX is to make it easy, to as far as possible make it automatic. So when an OpenType font family has optical sizes, has different outlines for use at different sizes, which of course we're used to from Computer Modern. Knuth did that years ago. CMR5 is quite different from CMR10. But original PostScript fonts didn't. You had a single outline scale to all sizes. Well, now optical sizes are coming back. And professional font families now do have optical sizes. So if I ask XeTeX for the font Brioso Pro at a range of different sizes, what we'll find is that it actually chooses different typefaces for those different sizes, from the caption face that it uses at 7 point up to the display face at 24. And that happens automatically just based on the size that was chosen. The information that controls that is in the OpenType fonts. And XeTeX is relying on that. So it looks at the font and it says, OK, for 16 point, which typeface is the right outline to use? As a user, you can override that if you specifically want to. If you want to use the caption face at 24 point, you could do that. But automatically, by default, you get the appropriate face that the designer chose for that size. OK, and then let's talk about installing a font. A TeX installation, of course, comes with a lot of fonts that are ready for you to use, like Computer Modern, but others as well. But if you get a brand new font that you buy or download and you want to install it, how does that work? Well, let's take Adobe Caslon Pro as an example. That's quite an attractive OpenType font. It comes with 6 OTF files. How do we install that to let TeX use it? Well, to be honest, I've never actually tried this because it's too difficult of a procedure. This is what you do, something like this. I don't want to try and go through it step by step, but I've looked in the TeX font installation guide and I have some idea of what's involved. And there are scripts that will automate a lot of this. If you know which script to run and where to find it, of course, it can be done. People do it. But a lot of users look at it and say, no, I think I'll just use Computer Modern. So it shouldn't be that hard. There shouldn't be a 100-page font installation guide to help you use a font with a typesetting program. A typesetting program should be all about using fonts, and it shouldn't be difficult. So the XeTeX way to install a font is to drag the font files to the font folder. It's the same as you do if you want to use the font in, I don't know, pick your favorite GUI application. Microsoft Word, OK, it's not our favorite. But you want to use the font in any other application on a typical computer. You put the fonts in the font folder. That's library fonts on Mac OS X. It's /Windows/fonts on Windows. It's ~/dot fonts on most Linux distributions, or /etc/share/fonts or something. Wherever your distribution keeps fonts, put the font files there. And it's ready to use. There's nothing else to do. I think, yeah, this would be a good point to stop, and let's try and actually do this live and see if it works. Let me bring up a TeX document. Let's do a couple of demos, actually, at this point. First of all, let's look back at Unicode support. Let's make the text bigger so you can see it here. If I can remember how to do that in TeX Shop. That big enough to see? Yeah. Okay, so looking back at Unicode support for a minute, this is a little sample file that's got a number of different languages and scripts in it. And if I simply run typeset on this, TeX by default starts out in Computer Modern, so it will try and typeset my document in Computer Modern. And a little bit of it appeared. Let's enlarge that. Okay, so we got the English, we got the exclamation marks, but the rest of these characters, of course, are not in Computer Modern, so they just go missing. And if you look back in the log, you see all these missing character messages because of all the characters that were not in CMR10. So we do need to use a different font. It's Unicode text, but we still need to use a font that's got the right characters. So let's try that. Let's switch to Keras SIL and see how that does. Well, that's a little better. At least the Cyrillic works now. We get undefined character boxes in some of these other languages. But that's how difficult it was to add Cyrillic support to our document. Just choose a font that's got Cyrillic in it. Let's try font. Try a font that might have some Devanagari characters in it. Oh, I didn't actually set the font. We're doing better yet. Now the Devanagari is also working. Let's try a Chinese font. And then our Chinese text, Ni Hao, should also work. Oh, that font also had Arabic characters in it. So we can now see the Arabic characters here. Unfortunately, they're not rendering correctly because the Chinese font, although it's got Arabic characters in it, it doesn't have any information about how Arabic script really works. So it just prints the characters one by one as if they were English. And that's not actually correct. So let's pick a real Arabic font. And here we'll have to tell XeTeX as well to apply Arabic script rules. Choose Arabic, typeset. Finally, our Arabic script is actually joining properly as Arabic script should. The words are in the wrong order, though, because the other thing we need to do for Arabic is to say right to left mode, to put the paragraph from right to left. Finally, we can actually greet the world in Arabic successfully. Well, I think that's still a lot simpler than it ever was to set up Arabic support in the TeX we used to know. Okay, so that's Unicode, different scripts and languages, working pretty much transparently just by choosing an appropriate font, nothing else to do. The text is just text, and it works. Let's try font installation as well. This document is the old sample 2e from the original LaTeX distribution. I haven't done anything special to it. And if we typeset that, Actually, that ran with PDF-TeX rather than with XeTeX. If you can read that in the log here, but that ran with PDF-TeX, and of course it generates the standard sample 2e document. We can run it with XeTeX, and the result is exactly the same. So nothing has changed. Computer Modern still works for an English document. But what we can do now, because I'm using XeTeX, is to use the XeTeX support that I'll talk a little bit more about in a minute for different fonts. So let's try Adobe Caslon Pro that I just mentioned installing. Let's see what happens. Oh dear. It says right down here, Adobe Caslon Pro, not loadable, metric file or installed font not found. Okay, I didn't have the font installed. So let's install a new font. Well, I've got the OTF files right here. There they are. That's the font files for Caslon Pro right out of Adobe's distribution. And I'll take that, drop it in my fonts folder, and let's try the document again. This time it works. And our document is now typeset in Caslon Pro. So that's font installation. It really is that simple. No font inst script to run or anything. Okay, let's go back to slides here if I can find them. So that was installing a new font and using it with XeTeX. And my claim is that that's much more accessible than the old way used to be. It makes it possible for the average LaTeX user to try a new font, to see how their document looks in a different font, something other than Times or Computer Modern. So let's talk about using LaTeX with XeTeX. There's a XeLaTeX command that's part of the distribution that works just as an alternative to PDF LaTeX. The result is the same. You get a PDF file, but the processing is done by XeTeX instead of by PDF-TeX. There's not really very much to say about it. All the normal LaTeX document classes and packages are still used in just the same way to control the format of the document, to decide how it looks. The key difference is that Unicode works throughout the system. Unicode input, Unicode fonts. No input enc package to try and interpret the input encoding into LaTeX commands or something. It's text that goes right through. It can work that way because LaTeX is really about document markup, document structure, controlling the layout, controlling the different paragraph formats and page formats and so on. XeTeX is about the character level, character encoding and fonts. And so these two are not in conflict with each other, they work together. There are some problems. Of course there are some problems. It wouldn't be a computer system if it didn't have problems. The main questions that come up, the main areas where people run into problems are when they're using LaTeX packages that tried to deal with text encodings in different ways in the old 8-bit world. So input enc is the main package that's used to support that. And that simply has no place in the XeTeX world. But old documents that used that may actually need to have those packages removed, commented out, in order to run properly. You can also run into problems trying to use special custom encoded fonts that are not Unicode compliant, don't work well with Unicode text. So that can get complex. The other area is on the output side. When we generate PDF output, we do it through a TeX to PDF, a DVI to PDF driver. And often packages that do graphics support, drawing packages and so on, are designed to work with one specific driver. They might be designed to work only with PDF TeX. They might be designed to work with the DVI PS, and then you use GhostScript. They might be designed to work with DVI PDFM. So there are a number of different drivers. And graphics packages need to know about the driver. And some of those packages won't work automatically with XeTeX because it's a different driver than they're expecting. That's particularly the case with packages that want to write PostScript directly. TeX users who have been used to using DVI PS to generate PostScript output work with drawing packages that write PostScript commands directly into that output. That won't work because XeTeX doesn't go through PostScript. It goes directly to PDF. So in that way, it's like PDF TeX, but it's not the same as PDF TeX. So that's an area where there can be compatibility problems. But to look at using LaTeX with XeTeX as the engine, well, you are looking at an example right now. These slides were made with the Beamer class for LaTeX running with XeTeX so that I can get the Unicode fonts in and so on. So this is how the document looks at the beginning, and it's a completely typical LaTeX document with a document class and some package declarations. And the result is the slides that you're looking at right now. So that's the integration of LaTeX with XeTeX. I do want to talk a little bit about some packages that have been written for LaTeX specifically to work with XeTeX. And the most important one of those, by a long way, is FontSpec, written by Will Robertson in Australia, a guy I've never met, but he's done a fantastic job supporting XeTeX. So earlier I looked at just how a XeTeX font command can access any font just by asking for it by name. But at that level, a font command just loads a single font at a single size. And that's not really enough for LaTeX. The LaTeX font world deals with lots of different sizes and styles, and they're all interrelated. And if I want to change my document to use, well, like in the case of these slides, instead of using CMSS or whatever the default would have been, I'm using Optima. But it's not enough just to load the Optima font at one size or one style. It needs to be loaded for every different size, for normal size and small and footnote size and large. And it needs to be loaded for bold and for emphasized. Usually in LaTeX, that's done through the font description files, the FD files, that tell the whole LaTeX font system what all the different versions of the font are that are used for different shapes and sizes. But setting all that up for a font is quite complex. There's a lot of information that has to be specified. So that's one of the reasons why LaTeX users usually only work with the font packages that were included with their distribution where someone has already done that work. To set all that up for a new font goes beyond most people's understanding. It goes beyond mine anyway. So what FontSpec does is it takes all that away and it lets you just use a single high-level declaration to say, I want to use this certain typeface as my main text font. And it will use the XeTeX font machinery to load that typeface in all the different sizes and styles that are needed. So to change a LaTeX document from the default computer modern to a completely different set of typefaces all that's needed is to say use package font spec and then set main font to whatever typeface you want, and that will load the body font, but it will also load the bold version, and it will load the small version for captions and footnotes, and it will load the big version for the title. It will load the italic version for emphasized. It'll find all the different variations of that. You can also control the sans serif font and the monospaced font. And so with these high-level commands, you can replace fonts throughout a LaTeX document. And that's what I did in the sample 2e just now, to switch the whole document with a single command to Caslon Pro. But font spec isn't just a simple interface to fonts, it's also a very powerful one. It provides options to give access to all the advanced features that OpenType fonts can have. Different optional ways of rendering the text, different language options, and so on. Will has written excellent documentation for font spec. I wish I had XeTeX documentation just as good. But within TeX Live, you'll find the font spec reference that gives many, many examples of how to use all the different features to access the different capabilities of an OpenType font. A few other LaTeX packages to mention as well. XeUnicode is very important for backward compatibility. This is by Ross Moore. Also, the Australians seem to be important here. LaTeX users, of course, or existing LaTeX documents have a lot of these escape sequences to access special characters, accents, and different European letters and special symbols and so on. And those escape sequences are all defined by LaTeX to access the right symbols in the computer modern fonts or the Latin modern fonts with all their different custom encodings. So what XeUnicode does is redefines thousands of those things to access the standard Unicode characters. So that with XeUnicode, it's possible to still keep the existing LaTeX markup in a document and have it print the right Unicode characters with a Unicode font. Just to mention a couple of the other packages that are out there specifically for XeTeX, that it's interesting to me to see what people are doing. Francois Charette has written a package called Arab XeTeX, which obviously is for Arabic, and it takes the same conventions that Klaus Lagali's Arab Tech package used, but again it converts all that to Unicode so that any Arabic Unicode fonts can be used instead of just the special Tech Arabic fonts that Arab Tech supported. So we can do Arabic script. It can be entered either in transliterated form or directly as Unicode text. We can even do something as complex as Urdu script. Oh, I can't zoom in on this, never mind. I'm going to blow that up. And these work through the Arab XeTeX package using the same type of markup as Arab Tech would have supported. There's also a package called J spacing, J for Japanese. Miyata Shigeru is another developer that I've never met but who's contributed greatly to XeTeX with the support he's provided for Far Eastern languages. What J spacing does is implements the very carefully specified rules of Japanese typesetting for how the spacing should work around punctuation marks or between Japanese and English. The text that's shown here is rendered without any special handling, just by printing a Japanese font with XeTeX. But by enabling the J spacing package, we get adjustments to the spacing, particularly around the punctuation marks. You'll see it after the commas. There's some additional space being put in there. And that's done without any markup in the text itself. The package does it by controlling the spacing between certain character classes. And there's now a similar package for Chinese as well, ZH spacing. So the Far Eastern users are taking the Unicode, the support that's in XeTeX, and then putting it together with their particular typesetting rules to build something that will automatically give good output for their languages. It's also been very nice to see that packages like TeX that are used for drawing are now learning to support XeTeX. So because the driver that we use in XeTeX is based on DVI PDFMX, which was an existing DVI to PDF driver, we support the same type of specials, the same type of graphics commands. And so this figure, which I stole off the TeX website, for example, works within a XeTeX document right here in the Beamer slides, just the same way as it works in standard LaTeX. But it's also inherited the Optima font that was specified for this document. So the labels here have come out in Optima. Various of the driver-dependent packages for LaTeX now do recognize XeTeX as well, so that they work correctly. These are some of the examples that I'm aware of where the package does depend on what the output driver is, but either the package author or as part of the TeX Live packaging, it's been configured so that when it's run with XeTeX, it does the right thing. It uses the right specials to control the driver and give proper results. Okay, that's enough about LaTeX support, I think, for now. I will just say a couple of words. Well, are there context users here? I don't know where context users are in the world. I know, obviously, the Dutch people are context users. That's where it comes from. I know very little about this because I don't use context. But I do know that Hans has implemented an XeTeX option in context. So there is the ability to use XeTeX as the typesetting engine. And if you do that, then it's also possible to use XeTeX font names, the human-readable natural font names to access fonts and to access the optional features of fonts. I really can't say any detail about it, but I know there's some information on the context wiki about how to set that up. There are some context users who are working with it, but I haven't tried that myself. Okay, let's talk about graphics for a few minutes. Another thing that XeTeX does is to build into the TeX engine some support for graphics in a way that TeX originally didn't have. So we can include a PDF document within a XeTeX document, a PDF image, using XeTeX PDF file primitive. And this will create a box within TeX that has that PDF embedded in it. Then because it's built right into TeX, it's possible for macros to examine the height and width of that box so that you can do layout with macros to fit the image into the document. For LaTeX users, of course, the graphics package has supported a lot of these things for a long time, but this is now part of the engine itself without needing additional macro support. There's a new feature in the current development version of XeTeX, which is that it can also find out the number of pages in a PDF document. And that allows you to write macros that will iterate over a whole document. So you could include thumbnails of another document within your file, effects like that. The PDF Pages package wants to use that feature Besides PDF, we can also embed raster images in several different formats. There's a XeTeX pic file primitive that does that. And again, just like a PDF, that creates something that TeX at the macro level can see and examine its size so that you can format based on the size that you see. The LaTeX graphics package, when you use include graphics in a LaTeX document, it is actually using these XeTeX primitives behind the scenes, just through the standard LaTeX syntax. On macOS 10 only, but not on other platforms, it's possible to support a whole range of other image formats because we have some support through the operating system for loading those. But for the sake of portability, I'd encourage people to stay just with the standard cross-platform JPEG and PNG that are supported everywhere by everybody. New feature that's just working. I think it's been possible for a while, but I didn't really know how to do it until just recently, was to support EPS images as well. That's something that's been, I think, a frustration for PDF-TeX users because PDF-TeX doesn't like EPS, whereas LaTeX and DVIPS, EPS was the natural format to use. So with XeTeX now, we can support both. We have PDF support directly, but we also have EPS support built into the output driver. It's actually done by using GhostScript behind the scenes to convert the EPS, but it works transparently so as far as a user is concerned, the EPS image is being supported directly. So that's an example that I threw in here just to make sure that it would work for me. And that's done with nothing more than an include graphics command in LaTeX and provide an EPS file. And behind the scenes, by the output driver, that's embedded into the PDF. Okay. Trying to remember what demos I was going to show as well. Yeah, let's do a couple more live demos just to break things up here. This file demonstrates the new feature that's used by packages like JSpacing to get spacing and other control in between characters of the input file. Let's make the text here a little bigger again. And I'll run this document right as it is. We get some missing character messages, and we'll see that in my source here, I've got a sentence that's just in English, that's fine, and I've also got a sentence where a couple of words are in Chinese. And that is a problem because the English font that I'm using doesn't support Chinese characters. So, of course, I get undefined character boxes. Looks very ugly. Now, I could go into the source here and add font changing commands around the Chinese words. That would be the typical thing to do, put some markup on there so as to change to a Chinese font for those words. But it would be very nice not to have to do that. It would be nice if the system could be configured to automatically change fonts when it needs to. And that's what this inter-character feature can do here. Basic principle is that every character is assigned a character class, and then XeTeX can be configured to look at the classes of the adjacent characters, and whenever it sees a pair of characters together in a certain pair of classes, it can insert some commands in between. And so this is set up so that whenever we have an English character followed by a Chinese one, we're going to insert a font changing command. And we'll do an end group when the reverse happens. So based on these character classes, we can get the font changes to automatically happen in the right places without having to go through the whole text and add markup around every piece of Chinese that was included. And obviously you could configure the same thing for Arabic or Hindi or whatever you might need to use. Another little example that's in here as well, let's rerun this now, is consider the case where we want to spread a certain line of text across the whole page, like maybe a headline across all the columns of a newspaper or something. What TeX will do by default is to just spread the spaces between the words, because TeX does not do letter spacing. That was Knuth's deliberate decision, and usually he's right. But there are some special circumstances where letter spacing is actually what you want as a special effect. And to do it just in TeX macros, it's possible, but it's very cumbersome macro programming, and it will probably break other aspects if you try and mix it with different macros. I know there's at least one LaTeX package that can do this, but it's quite fragile. But with XeTeX, now with intercharacter tokens, I can tell it that between every pair of characters of class 0, that's the English ones, I want to insert just a little bit of space. And if I do that, without changing the text, and without any active characters, without any macro programming, I can get those characters to spread across the line. So that's just an example of the control that you can get to affect formatting by inserting implicitly at places in the source where there was not any actual markup. And that's how the J spacing and ZH spacing packages work. They use this feature to detect the transitions between characters, punctuation, English characters as opposed to Chinese characters, and so on. They detect all those transitions and insert commands there. Another example of that is, this shows again how that can affect something like Japanese typesetting. So this is Japanese text off of the Unicode website. And this is set just by default in a single Japanese font. The Japanese font has English characters in it, but perhaps that's not the style of English characters I really want to use. So again, by using intercharacter commands, I can switch wherever there's a transition between Japanese and English. I can switch fonts so as to use the Optima font as my main body font for English, but then whenever I hit a Japanese character, we'll switch into the Japanese font. And that should give me a document where the English is now in Optima and where the Japanese is still in Hiragi no Kaku Gothic. And again, I did not have to go and add any font switching markup within the document itself to make that happen. It's all based on XeTeX knowing the classes of the different characters and detecting when that changes. Okay, let's go back in here. And let's talk about math for a minute, because TeX users usually like math. When you do math formatting with TeX, I don't know how many people have looked in detail at how TeX the program works. Obviously, as a user, you don't usually do that. but a whole math formula is read by TeX and converted into a math list that is a tree of all the different pieces that make up that formula and how they relate to each other. And then TeX has this algorithm that Knuth worked long and hard on that walks through that tree, converting it into horizontal and vertical lists, the things that TeX knows how to place on the page. And it chooses the right style, the right font for each character in the formula based on what it knows about that math character. That's all based on 16-bit codes for characters that contain a type of what the character is, whether it's an opening delimiter, a closing, or an operator, or a variable, or different classes of things that are formatted differently. And then there's a family which controls which kind of typeface is used, and there's an actual character code. Then we have things like delimiter and radical that are a little more complex and bigger. But the other thing that's used then is font metrics. There are a number of special dimensions in the math fonts that TeX uses to control the spacing of the various different elements of the formula. There's a special font dimen in the math symbol font that controls how thick the fraction bar is, or how much the superscript should be raised, or all these different details of exactly how math is formatted are specified in the font metrics of the math fonts that Knuth made, and a few other math fonts, of course, have been made to the same specification. Appendix G describes exactly how all this is done, step by step. So to be able to do math in a Unicode document, well, because we still support all the old TFM files and TeX fonts and so on, you can still use all that. But to do Unicode encoded math, the whole mechanism needs to be extended. So instead of 8-bit character fonts in the math 8-bit character codes in math fonts, we need Unicode character values. And we need to be able to define the math behavior, not just of 256 characters that might be in an 8-bit document, but of the whole Unicode range. So one of the major things that I've done with XeTeX is to extend all those math processing tables to support the full Unicode character range, and provided new primitives for setting those values, so that we can say that the integral command accesses a certain Unicode character, not just an 8-bit code. Some examples of what that looks like. It's just like the macro code that's in plain.tex, or it must be somewhere in the LaTeX source files as well, for setting up math codes, defining math characters. It's very tedious. No user should normally have to do this, but somebody has to decide how every math character is to be treated. And it's done by setting these math code values for all the characters. Then we also have OpenType fonts for math. This is a very recent development, because it's only really with Word 2007 that Microsoft has decided exactly how OpenType should handle math. And the good news is that what they did is a really good job, because they studied TeX very carefully. They worked with Leslie Lamport, I believe, and other people who know TeX very well. And so what they've done in OpenType for math support is very much compatible with how TeX works. All the same information that TeX wants is there in an OpenType math font. So with an OpenType math font, we no longer need a TFM file that has all the special font dimen parameters that TeX uses. That information is built right into the font in a special table in the font file. Microsoft released one along with Word 2007 and a number of other products, and that's Cambria Math. Apostolos Riopoulos in the tech world has done a math font as well. The Styx fonts that are in development at the moment should eventually have this OpenType math support as well. So it's only just beginning, but there are eventually going to be a whole family of Unicode compliant and OpenType based math fonts. And then it should be possible to use any of those with XeTeX through the same set of Unicode math character definitions. So right now it does work. The only limitation is that there are not very many fonts yet. But this shows an example formula that I think came out of the tech book, if I remember right. First in computer modern, the way tech traditionally has made it look. And then the exact same math formula formatted with Cambria Math, which has quite a different look. But the behavior is all working just the same, but all under the control of the OpenType font. So that's what's coming in Unicode Math, and I think we're not very far now from the day when it will be possible for all our mathematical data to be encoded in Unicode, which makes it much more interchangeable with the rest of the IT world and with standards like MathML that are all based on Unicode as well. I can actually show math working as well, I hope. Yes, that one should work. So, there's my font size. Okay. So this is just typical tech math markup. These are all samples that I lifted straight out of the tech book, so there's no cheating here. But by loading Unicode math definitions for the Cambria font, I can typeset all these standard tech markup in Cambria, and they should all work. So that's the kind of results that you can get. This top one I've repeated. It's in there twice, and they come out exactly the same. But if you look at the source for this, you'll see that the two versions are slightly different. One of them is the standard tech markup. But then here in the second version, is this big enough to see? Let's make it maybe a step bigger yet. In the second version, I've put in the actual Unicode characters for some of these elements, like the sigma, and the infinity, pi over here. So the Unicode character works just as well as the tech command. And if you're getting math data that's not being typed by a tech typist, but maybe coming from some other system, it may come in Unicode form. And the result now can be exactly the same without any special macro processing or conversion. One of the great benefits of tech going to the Unicode world is that it's going to give us so much easier interchange of our data with people outside of tech who never used / this and that. We don't have to anymore either. You still can if that's the convenient way to type. So that's, okay, Unicode Math. I just have a couple more slides here, I think, and then I'm going to see if people have questions as well that you'd like to ask. Yeah, just a couple of comments for people with a technical interest about how this works inside. How does XeTeX actually work with OpenType fonts that the operating system controls, that are really outside of the tech world? The key idea here is that there's a new data type inside tech, a new node type within the lists that tech builds, that I call a native word, which is a fragment of text that's being rendered with an OpenType font. So what tech normally does is it collects characters one at a time, and it knows the dimensions of every character from a TFM file, and it lays out the characters in the line. But with an OpenType font, there is no TFM file, and TeX doesn't know the dimensions of each character. And it can't know the dimensions of each character because the character might change. You can't just look up the size of the F, because if it's followed by an I and you form an FI ligature, it may change. So it's not an option to just cache a whole set of character widths. There's a more complex layout process than that going on. So what XeTeX does is it takes a whole word or a whole run of text that's being rendered with a single font, and it treats it as a unit. Within that unit of text, it will call the OpenType layout engine to do all the calculation of exactly which glyphs from the font should be used and how they're going to be positioned. And then when TeX wants to lay out the paragraph, that word is just a single unit with a certain size. So when you look at how the structure that's going into a paragraph, in traditional TeX, we'll have a sequence of individual characters, each of which has certain dimensions, and then some glue in between for the spaces. But with XeTeX, that same text will become not a sequence of character nodes, but a sequence of word nodes, and then between each word there'll be some space. And then within the word, we can call the OpenType font engine to say, okay, given this whole word in a certain OpenType font, figure out how to draw it. One thing that complicates a little bit is hyphenation, because TeX doesn't see the individual characters anymore. It only sees the word as a chunk. So if hyphenation is needed, then we actually have to go back and take those words apart again into smaller fragments and put discretionaries in between. Because when TeX runs its line breaking pass over the paragraph, a discretionary is one of the places where it could break. So some people probably are familiar with the idea that TeX always first tries to lay out a paragraph with no hyphenation in a first pass. And then if that doesn't work, then it goes back and looks for places that it can hyphenate and inserts discretionaries. And it's at that time that I have to go in and take these words apart again and make word fragments out of them with discretionary breaks in between. So that works. You get results like this, because then the line break routine can find a discretionary break and use it if it needs to. And if it doesn't use it, then there's no text at that point. It's not quite perfect, though, and this was one of the early bug reports, because if you look closely at the word differ there, the FF ligature hasn't happened. And the reason that hasn't happened is because there's a discretionary break in between. And that breaks the OpenType layout process, because the OpenType layout process doesn't know anything about the discretionary. So what we actually have to do then is, after we've chosen the line breaks, any discretionaries that weren't used have to be taken away and put the word fragments back together again. So that's actually what happens now in XeTeX, and the result generally is exactly what you'd want it to be. But it's a little different behavior than TeX used to give, and it means that there can be cases where if you used just maybe open brace, close brace to prevent a ligature in TeX, that might get thrown away and the ligature could reform in XeTeX. You have to use something a little more robust, like maybe a zero-width kern. Okay, that's enough slides, enough talking from me, I think, for now. But I know there's at least one or two questions, and I'm happy to try and answer anything that anybody would like to ask.